This is Exploiting USB Devices with Arduino with Greg Osa.
Thank you everyone for showing up after lunch. I appreciate it. So today we're going to be talking about, really how to go about doing USB assessments, getting to the point of, really how would you go about exploiting things over USB? What hardware can you use to kind of instrument the USB protocol? Just to kind of start off though, I kind of want to talk about my daily life. I work as an application security engineer, and basically it's the equivalent of an application security consultant, but on a different line item on the bills. And really what my day kind of looks like is usually I'll stroll into work, sit down in front of an HTTP proxy. Sometimes maybe not an HTTP proxy, maybe I'm looking at a custom network app or something like that, so maybe it's a custom proxy. Then I just sit in front of a web browser all day, pretty much clicking things, typing things, breaking things eventually, right? I'm sure many of this sounds a little bit familiar for people who really do application security. I mean, you're kind of a glorified web browser, just clicking things, and then eventually have to report it, and then the day continues, really. So, that's just kind of how the industry is right now. As companies develop their own customized applications, kind of the easiest way to distribute that across a large population of people is on the web. So in doing application assessments, really my day is full of web applications. Like I said, sometimes the custom network client-server application, which is great. You get to do protocol parsings and things like that. And you might be saying, well, Greg, that's not very impressive or interesting, and why are we all sitting here talking to you? Well, to talk to that, we're going to have to go back probably about 3 or 4 months ago. And suddenly one day, as I was doing a web application assessment, a device landed on my desk. It's called the Screen Keeper device. And it made promises such as protect the privacy of your computer monitor, and safe, secure, and automatic. And kind of those 3 words together scare me because I really don't think automatic with anything when it comes to security. So actually what this device says it does is, you plug in this USB device into your computer, and you have this wireless token that you clip onto your belt or your shirt, and when you walk away from your computer, it locks your device. So this is kind of helping enforce the common policy of, lock your screen when you leave your computer, and given humans, that never happens. So this is what this device is looking for. This is what my company was looking to kind of use this device for. But it landed on my desk because obviously with claims such as this, you can't always take their word for it. So really the question became, well, what does this actually do? How does this actually go about enforcing this policy, enforcing the fact that the screen is going to be locked? And, coming from my weeks and weeks and months of looking at web apps, I'm like, well, how do I even go about assessing this thing, right? It's USB, that's cool, but how do I actually start looking at this traffic? What's the equivalent of burp for USB? Am I going to need hardware to look at this? I'm going to have to go out and buy a GNU radio to look at this wireless traffic. Really, it's kind of almost a daunting task to say, well, you're used to looking at this, you're used to doing these similar things day in, day out. How do you actually shift gears and then start looking at, something that's, kind of as trivial as this little device? That's what I'm going to talk about today, really, is, applying kind of the common steps you would take during a network or a web application assessment, applying that directly to, USB devices and looking at USB traffic and things like that. And then, that kind of helps you gain an understanding like you would in a web app. But then let's say you do find an issue. How do you go about exploiting that? How do you go about instrumenting that? Sure, it's easy to sit down in front of a web browser and make requests, or sit in front of an HTTP proxy or a custom TCP proxy and make whatever request you want to. But how do you go about making requests over USB? So I'm going to talk to that using cheaply available hardware to do that. So that's what we're going to talk about today. And to get started, of course, before you can really dive into any assessment, you really need to have an understanding for the protocol that it's talking, right? You wouldn't assess a web app without understanding HTTP, or I guess you could attempt to do a web application assessment without understanding HTTP, but you probably wouldn't get very far. So just kind of a high level. Again, I'm not an electrical engineer. I come from a CS background. I'm not very good with current and voltage and things like that. So really the USB primer here is really kind of a high level because it's not so much the underlying protocols that we care so much about. It's really kind of the application level protocols we care about. So, just like in network stacks, you might have, TCP on top of IP, and then really what we care is about the HTTP traffic on top of that. Same thing with USB. It has a number of different protocols, and they build upon each other. You have your base protocol, and then on top of that, you have class-level, basically, protocols that define, oh, this is a keyboard, so we have a standard way to communicate for that as a HID class. So there's different classes built on top of that, and then again, on top of that, you kind of have your application layer protocol, right? It's what the device is actually sending its data across, and it's saying, it's data, in a specific format that it understands to execute its functionality. So one great reference I found for the USB protocol, and it really helps distill down kind of the US spec is, a very large document, very dry, and talks about things related to current and voltage, which, is interesting, but not necessarily core to begin assessing these things. So the Beyond Logic site has kind of a nice guide to distilling down that protocol spec to really understand the core protocols and the core things happening in USB. So back to kind of, well, this device is sitting on my desk. I kind of have a little bit of a primer. I understand, at a high level what USB looks like, what's involved. It's kind of just like, let's just dive in and see what that looks like. So how do you even go about assessing that? And kind of my approach in doing this is really go with what I was comfortable with, what I did day to day, really. And that's breaking down an assessment really into familiar steps. So this gets into the dry, boring stuff that you see all the time, right? Threat modeling. Kind of a first step. Sure, we have this hardware device. Really identifying the different components that are part of that architecture. Identifying then with those components, what are the security relevant use cases? What's the functionality? What are the actions that this device takes that I actually care about? And then from that, really, what are the trust boundaries that are established between those components? Either be it explicit, obviously, we can assume maybe this wireless dongle that you're taking with you hasn't been compromised. As an explicit trust boundary, what are some of the implicit trust boundaries? And then once you've kind of identified the different use cases, really going through and doing an analysis of that. And this is where it becomes really important to, be able to view the protocol and view the traffic. So really identify the inputs and outputs for those use cases that were previously identified. Identify, how is this data packed? How is this data stored and transmitted and read? And how are these actual use cases executed in between all of the different components of the system? And then from that, we have stimulus response testing. So this is really then going ahead and instrumenting that testing. So now we understand the protocol. Now we understand what it's doing. How do we go out and actually make requests against either this host device or this wireless device? How would we go about actually running our own test cases that might deviate from the expected test cases? And then finally, as the last step, is really exploitation. This is, maybe you've identified vulnerabilities. Maybe you've identified something, maybe you have to chain multiple vulnerabilities together, but really packaging all of this together, making sure all of our required conditions to execute this vulnerability exist. And this is what I call the ponin suckas phase. So this is where it actually gets fun. In the end, you have something that's packaged together. You can show it off to all your friends, make a video or something like that. So it's really tying all the hard work together into something interesting. So really, we're going to step through these different steps in looking at the Screenkeeper device, the things that came up, and really the end result of ponin suckers. So this is all boring, I know. You're probably wondering, well, I want to go justify buying an Arduino, so what are we going to do? It's coming up, and like I said, it involves part of the exploitation phase, so it should be an interesting kind of end result. So back to threat modeling, right? We have our different components of the Screenkeeper architecture. There's this wireless token that's shown with kind of the silver. That's like a clip, so you can clip it on your shirt and be super fashion forward. There's a USB dongle, and this is the little USB that plugs into your computer. And then there's software you run on the host. And kind of in noticing this, the host software is completely user space. It doesn't install its own driver or anything like that. Part of the packaging says the wireless token goes over 2.4 gigahertz. It has some mention of AES. So maybe they thought about security, things like that. So just this really kind of the different components of the screen keeper device. And then working through that, this is kind of the equivalent of you're working on a web application. The first thing you're going to do is log in, go through the functionality, really try to identify all the different functionality that's there, identify what inputs required, how do you actually go about executing that functionality and things like that. So really taking the same approach with this hardware device, you can go through, and I went through kind of the different use cases, the typical installation and usage. So installation basically, like I mentioned, you really don't have any hardware OS drivers to install. Instead, you just run this software that runs as a tray icon. And during this installation phase, you also enter in an override password. It's a password that you can enter to override the login, override the need for a token to unlock your screen. And it's separate from the Windows login password. Like I mentioned, this has no integration with the Windows accounts or the integrated auth or Gina or anything like that. So that's kind of the initial installation. Then as far as, kind of the big use cases, right? The first is, how do you lock the screen? What happens when you lock the screen? And how do you go about unlocking the screen? So there's two different ways to lock the screen. The first is you have your token on, it's synced up with the software, and you walk out of range of your desktop. And after you've gotten, somewhere around 15 or 20 feet, the screen locks. And it displays this overlay with, it's kind of like a screensaver, but not a real screensaver. It just overlays your desktop, speaking of how it's protecting the privacy of your computer. And when you walk back in range, then your screen unlocks. So this is the kind of the core functionality, the core use case of this device. You can also kind of simulate the exact same thing by just turning the wireless token off. There's a switch on the side. You can switch off the token, and then it will lock the screen, and you switch it back on, it'll unlock. And then kind of the last way that we really won't get into too much, but to unlock the screen, you can also enter in, again, that override password you had supplied into a dialog, and it'll unlock the screen. So really, again, just... No, it's not using it. Actually, in the documentation, it explicitly says that if you're running it, it will disable the screensaver for you. So there's not any sort of confusion of having a Windows login as part of protecting the privacy and security of your screen. So yeah, that's a good point. There's no integration with those Windows login, which I think just as initial kind of sniff test, I'm like, oh, this seems interesting. I think I would have, obviously integrating with the login would maybe proved a more mature product in that. So, but that's how it works. I didn't really do much of a deep dive into the software, and this is just an overlay. Is there some way to escape out of that? Typically, how those things work, the answer is yes. But really, I was kind of focused on the hardware on this. So those are the kind of the typical installation usage, just to kind of build out our use cases. So again, the use cases that obviously come from this are pretty much what we talked about. Somehow the device is installed, it's registered. Another use case, you lock the screen. The other use case, you unlock the screen. So here really, we have these different components, so we can kind of break them into our different trust boundaries, right? What are the different components, and what's kind of the assumed trust? Where does the trust either be elevated in between the different components? And one is the host to the USB receiver, right? In this architecture, in kind of the attack surface of this device, you're assuming that the host software hasn't been compromised, right? Because if the host software is compromised, or if you can compromise the host software, there's really no need to lock your screen because the software's already been compromised. So that's kind of the first trust boundary. The two components that talk to each other, right, is the software running on the host and the USB receiver. So that's kind of the first trust boundary. Kind of the second trust boundary then is we have this USB receiver talking to a wireless token, right? The wireless token is assumed to not be compromised. That's on someone's person. They've left, and now kind of the attack surface really is that USB receiver, that host software. So in doing this, and this is actually one of the more interesting things in doing this for me, is when you do a network assessment, a web application assessment, you never think really of the fact of like, oh, someone can bust into the data center, rip out the rack, and pull out the hard drives. Where in something like this, when you're dealing with physical devices, you always have to kind of take into kind of the physicality of these devices that it could be compromised. So really here we can kind of assume that the attack here is someone going up to your desktop, trying to get access to your desktop, so that USB receiver could be compromised. The physical host obviously could be compromised, but we're not talking about, again, ripping out a hard drive or anything like that. So really, one of the important things to note is the USB receiver that's plugged in the computer itself needs to be considered compromised in the architecture. So now, since we've kind of established our use cases, the different things that we really want to understand how they work, we need to go about doing some sort of analysis of that. So how do you go about actually getting access to the traffic that's over USB? How do you go about actually identifying what information is actually passed across these trust boundaries? So to do this, basically, there's a couple pieces of software or hardware you can use that basically is going to give you a log of all of the traffic, really kind of help you decode and understand that traffic that's sent across the USB bus. So on the hardware side, a couple of the common ones are the Total Phase Beagle device is one of the lower cost hardware. Elysis, actually MQP Packet Master does both analysis and generation of USB traffic. Then this one looks super expensive, LaCroix, I think. So in general, the hardware components cost a significant amount of money and represented by exactly 5 bags of money. So in general, it's not the cheapest way to go about assessing these USB protocols. It's great, and actually what seems to happen is the price of these devices starts more and more increasing as you get into basically faster protocols. So USB 3 is going to cost you a ton if you actually want to assess that, because the hardware required to keep up with that speed is more expensive. So just some of the, but if you're in the situation where you need to assess that, you might have to spring for that hardware. So there's also a couple of different basically commercial software available that hooks into the operating system and logs the information that way. Typically these are for Windows, so there's a couple for Windows. Actually in Linux there's open source USBmon. It'll help you log traffic that's sent on a Linux host. But in general, software the commercial software is still somewhat expensive. You can do the open source stuff as well, USBmon. But in general, what this doesn't buy you, that hardware buys you, right, is let's say you want to assess traffic between an Xbox and a Kinect, right? You can't run software on that Xbox to log its USB traffic. You need to get a physical device in between that to really do the analysis of that. So that's just one of the areas where software might not be feasible to do this analysis. Kind of the last thing I'm going to talk through, and basically what I'm going to present, and it's kind of a really easy way to do this, is using virtual machines to actually go about and log USB traffic. As part of your virtual machine, right, you have your virtual USB interface. And you can enable debugging logging on that to get a log file that's basically a dump of all the USB traffic that went across that virtual interface. So they actually have a nice kind of front-end client for these log files called VUSB, or Virtual USB Analyzer. It's open source software. You can use VMware Player. So really it's kind of a free solution to go about and do to get logs of this traffic to begin your analysis of these use cases. All right, so just in general, I'll just kind of breeze through this. All you really need to do is just change your configuration file to enable debug logging for USB traffic. Once you set that, you just basically plug in your USB device, hook that USB device up to the virtual USB interface on the VM, and you get a nice log of information that you can parse through. So now, since we're kind of armed with the ability to go through and really observe the communication over the USB bus for our different use cases, the next step is just to start stepping through those use cases and really identifying what the functionality does in general. So kind of the first question is, how do you go about actually registering a device, right? You can assume there's multiple of these devices in existence, so how do you go about actually registering this device with a specific host? So this device unlocks a specific computer, right? So the first test, of course, was, well, we have 2 of these devices. Let's plug one in, register on the computer, unplug it, and plug in another one and see if it unlocks the same computer, right? An attacker could do that. They could be in possession of another set of these wireless tokens and USB devices And unfortunately, that didn't work. I mean, I guess fortunately, because if that worked, then this would be a really boring talk. So it's the case that, no, they are uniquely registered. They are uniquely paired. So obviously, the next question is, well, how is this registered with the host? And aptly enough, it uses the registry. So what we actually get stored in the Windows registry is this value. It's a 22-byte-ish or 22 hex character Unicode string that's stored in the registry. And this is basically for each device you plug in. The first one is written into the registry. Any additional device you plug in, it will not be written to the registry. So it's kind of allows you to register a specific wireless token pair with a host, stores it in the registry, and then each time a new device is plugged in, it's checked against that registry to make sure that, yes, this is the same device we saw before. So it's part of the software that runs. So that software monitors basically when you plug in the device, it then writes that to the registry if it doesn't already exist. So the next question is really, well, we're plugging in this USB dongle. What information is actually being sent? What unique information is being sent from that USB dongle to do this registration? So really, what information is being sent from this USB device to register it? And as part of that, as part of the USB protocol, there's a phase of that where basically you enumerate the USB device descriptor, and this includes things like the vendor and the product ID and all sorts of things, basically the generic information for that device. One thing we can kind of see here is, obviously the kind of the interesting ones is, the product screen is the screenkeeper 1.0a, and then you have the serial number string, which is actually the same. It's the ASCII version. Well, actually, it is Unicode in the descriptor table too. But it's the same value we saw registered in the registry. So basically what's happening is you plug in a USB device. It's going through enumerating this USB device descriptor, and it's storing that value in the registry if it hasn't been registered already. If it has already been registered, it's checking that value to see if it's going to accept messages from it. So now we've kind of, without even looking at USB, I guess this is a little bit of looking at USB, but you can pull this up in the control panel if you want to. Really without looking too much traffic, we have an idea really of what does device registration look like, how is that performed, and how are these uniquely paired per host. So the next question is, well, when the host screen is locked, so when we have a screen that's locked and being protected, what does the USB traffic sent look like? What is this device doing to say, hey, this wireless token's out of range, lock the screen? What's being sent? And actually the answer to that is no traffic's being sent. So really it's the lack of USB traffic that's signaling to the host software that the screen should be locked. So we can identify that, right? And then the next question is, again, it would have been kind of a funny finding, but it wasn't the case of, is this kind of like a fail-open system? If I just walk up to something and rip out the USB devices, like, I don't know what to do, and unlock. And that's not the case. But again, something else to test. It would have been kind of funny, but it's not the case. So really, and then kind of the last question, and we talked about kind of, we're assuming the USB dongle can be compromised, but they could do something to prevent that, right? They could say, if this USB device if the screen's locked and the USB device has been unplugged and then plugged back in, don't trust it, require someone to enter their override password. Something happened to that dongle in the period of time since the screen was locked. So that's kind of the next test case is, can you go up to a machine, remove the USB dongle and plug it back in and have everything work as normal? And the case is, yes, you can do that. So now we've kind of solidified the fact that that USB dongle can be compromised. It's fair game for an attacker to go up, grab that dongle, walk away, and do whatever they want to with it. All right. So now we kind of understand what happens when the host screen is locked. The next question is, of course, the million-dollar question is, how is the screen actually unlocked? What's being sent across USB to say, hey, unlock the screen? And what we're actually getting in is a HID report in. And as part of that device descriptor and part of that enumeration, this enumerates as a HID device. And this kind of plays to why a device driver isn't needed. It's just using the same protocol as your keyboard or as your mouse to go about and send data. And that's fine, but as part of that enumeration, you define a HID report. So basically it's the structure of information that you're going to send across in these messages. And what we get is really kind of the first giveaway that this might be a bad thing is we're sending a static message. No matter how many times we've unplugged or gone in range or not in range, we're sending the exact same message over and over again to unlock the host device. And we can see here there's actually 24 bytes of static data that's being sent per token to unlock the device. So we can kind of look at those 24 bytes of data that's being sent. So this is looking maybe a little more familiar, right? It looks like, okay, well, we have some ASCII text followed by nulls, likely maybe a Unicode string. So if we go ahead then and decode that as Unicode, it's actually the exact same value that we had before with an 01 tacked on, probably just to make it 24 bytes. So kind of looking back, I think that was stored in our registry, which is fine. We can't compromise the registry. But also, that was disclosed in our USB device descriptor table. That's on the USB device that someone can unplug and plug into their own computer. So what again was that secret sauce that's used to unlock the host? The serial number from the USB descriptor? So really now, this is kind of, and this is surprising. I mean, this is surprising to me because I'm looking at this device. I'm like, oh, there's all this electronics, and I'm just like, this is really. They really kind of took the fact of like, no one's gonna figure out this USB bit. Like, no one's gonna look at this. So really, in summary, we have something where the USB receiver can be compromised. Basically, we lock based on lack of traffic. We unlock based on some static USB traffic. It authenticates to unlock that based on the USB serial number. And anyone can grab that USB serial number out of USB descriptor table, right? So this is the equivalent of your Post-it note with your password on your monitor, except instead of a Post-it note, it's a USB dongle. So now we've obviously, we've identified a vulnerability here. This is this is broken. I can go ahead and not recommend this. But then the question becomes, really, how do you go about testing this? How do you go about instrumenting something that's going to act just like this device? Obviously, there's a vulnerability here, but how would you go about exploiting that in the real world? So we know exactly what we want to do. We want to go up to a user's computer, unplug their USB token, read the serial number off of it, create some sort of device that's going to replay that message and enumerate with the same device descriptor as that device, and then we're going to pwn them and steal all their sensitive information and profit somehow off of that. So how do we go about doing that? What are the steps we're going to take to do this? And this was kind of my like, well, maybe I'll just write the report and call it a day. It's obviously bad, but definitely kind of got me thinking. How would you go about doing this? How would you go about instrumenting this? So we have the first step, right? And that's reading the serial number. So obviously, we can become real USB hackers by running something like LSUSB or System Profiler or using the control panel in Windows. So first step, obtaining the serial number is pretty straightforward as long as you know how to unplug and plug in a USB device. So we can pull the serial number directly off of that descriptor testing. But obviously the more important thing is how do we create a device that's going to send the serial number in HID reports? And that's where the Arduino comes in with lightning bolts. So in testing here, and actually it's kind of important when looking at Arduinos and the chipsets they have, the Arduino Uno was actually one of the changes they made in the latest version was to use the ATmega 8U2 chipset for USB. And this is really nice and really convenient because there's an open source, and actually what Arduino uses is an open source USB library called Lufa, or the Lightweight USB Framework for AVR. So basically this is a library, this is a framework where you can modify or do whatever you want to in the USB firmware, compile it then. You can flash it onto the Arduino if you give it the super secret handshake to turn it into the DFU programmer mode. Then you can upload your firmware and run your custom firmware on the Arduino. So that's exactly the route I took, and kind of the steps I'm going to go through here is how do you go about modifying that firmware, creating a custom firmware, flashing that firmware to really kind of do the simple steps we need to go through and accomplish. So the first thing you need to do is to get the Arduino into the DFU programmer mode. There's a couple places that you touch to ground. Again, I'm not an electrical engineer. I don't really know what it's doing, but that's what happens is if you bring those two to the ground, basically, instead of enumerating as an Arduino Uno, it'll enumerate as an Arduino Uno in DFU mode. And then you can use a tool called DFU Programmer, point it at a firmware file in a COM port, and it'll go ahead and upload that firmware onto the Arduino, or onto the ATmega 8U2, and then it'll continue to run your code. So starting then looking at the custom firmware, where do you actually go about modifying this firmware? making your changes to really make the device do whatever you want to. So a good place to start is actually Arduino has part of the Lufa source code distributed with their source code. All of their sources, I believe, open source, so you can download that. And really, there's only 2 files, luckily, that really matter when you're modifying or creating these firmwares. The first is descriptors.c, and this is basically the code that defines what's going to be sent back when a query is made to pull the USB device descriptor table. So obviously our first step is we need to go through and make this device look just like the Screenkeeper device that was plugged in before. We want to have the same serial number they had to make sure that when we plug it in, we're registered and we match the registration in the registry. And maybe they're checking, they're obviously, this is generic to all HID devices, so they're probably looking for a specific vendor ID and product ID to say, yes, this is a device I want to read traffic from. So kind of the first thing we need to do is to modify that descriptors.c to enumerate with our device descriptors. And then the second file is, and it varies for the different projects, but the Arduino USB serial.c is basically kind of your main loop of the firmware. And actually there is a main function that has a loop in it. So it is honestly your main loop of the firmware. And this is really where we're going to want to modify to go about and send that data packet, that HID report, with the serial ID that we took off of the host. So to kind of detail those changes, how do we go about modifying that? So since this is a HID device, so the source code that ships with Arduino is actually a USB serial device. So it has all the firmware to act as a USB to serial kind of bridge. That's not what we want to do. We know we want to enumerate as a HID device so we can mimic the same device as before. Luckily, Lufa is fairly complete in all the different examples it has for different class devices. So you can pull the demo code that they have for a generic HID device. So the next thing we need to do is once we have that source base in those examples, we can go through and basically modify all of the descriptors to match what was enumerated before on the actual real Screenkeeper device. So this is the vendor ID, the product ID, modify the section of code that responds to, what are your different report types? Say, well, we have this 24-byte report, HID report type. You also need to supply that. So that's defined in the descriptors.c as well. And then finally, we need to extend, by default, the HID example in the Lufa source code doesn't include any support for the serial number field as part of the device descriptor table. So we have to add code, basically store that in memory, create a reference to that, and then modify the callback USB get descriptor function when that's called for a specific index that we've set up as a serial number index. We want to return that value out of our program memory. So we can set up kind of those 3 things and plug it in, and if you're looking at the USB traffic for that enumeration of, you initially plug in a USB device, what does the device descriptors table look like? That would look exactly like what would happen for the real Screenkeeper. So that's kind of our initial modifications to make an evil descriptors.c in the Arduino. Oh, that's the serial number. I always forget I had that in there, so it just flies by. All right. So the next modifications we need to make too is actually the main loop of the program, right? So this is where we need to go through and actually send that data packet to the host. So the first thing we need to do, and actually this is one of the more frustrating things I ran into using the Arduino, is the ATmega chip does not have much memory on it. And really it has about enough memory to fit exactly what they were doing in it. So anytime you go through and actually are modifying or making firmware, you really need to trim it down as much as possible. Otherwise, when you go to flash it, you'll get an error that you're overwriting the bootloader code and it failed and things like that. So you really need to be conscious of everything you're doing in the actual program of this. So kind of the first thing is to go through and remove all of the unnecessary functionality. In this demo, there's a lot of things to blink the LEDs and things like that. So all of that can be ripped out to make room for the exact code we actually want to do. And luckily, we don't have to be super awesome programmers to do exactly what we want to do. All we have to do is just do one thing, and that's write that message to the host device. So in Lufa, you can use the endpoint write pstream LE for little Indian function. Basically, we give it the serial number plus our O1 as the value, and then we give our serial number length. And then we don't have any callback because we never really care if what happened at the end of these writes, so we don't set up a callback. So really, that's all we need to do. To modify our Arduino, go through, make sure it enumerates the same as a screenkeeper device, and then go through and send the packets and the information that we need. So usually software demos are completely horrible and fail about half the time. And I figured it would probably be, I would probably have about maybe a 15% chance for a successful demo involving hardware. So instead we have a kind of a nice reenactment of what the exploitation of this would look like. It's all real. It's not fake. But we have Mr. Manager here working on his top secret document at the desk. You can see we have super confidential information and the PowerPoint, just hard at work. And all of a sudden, a meeting request, right? So he's like, well, I was in the middle of working on the top secret stuff, but now I got to stroll out to my meeting. So let's go ahead and leave the desk. And like any manager, does not lock his computer. But luckily, he's armed with the screenkeeper, conveniently tucked into his shirt pocket, right? So as he's leaving his desk, he's like, oh, who cares if I left my confidential information open? Wait, protected by the screenkeeper. So we can see here there's a very serious looking lock on the screen. We have a message, you probably can't see it, but it says something along the lines of, your super private information is being secured by screenkeeper, no worries. But there are worries, because there's evil hackers on the loose. And that's Greg in a hoodie with a bottle of Mountain Dew and an Arduino. It's either a hacker of sorts or some sort of futuristic druid. I couldn't figure it out, but yeah, it's a little embarrassing. But I have my Arduino, my MacBook, and Mountain Dew like any good hacker, strolling the office looking malicious, ready to pwn some suckers. So first step, of course, is removing that device, shown here, drinking more Mountain Dew to make sure I got the evil juices flowing, and then plugging in the Arduino, right, because we need to actually get this in flashing mode. Once we do that, plugging in the USB device that we took off the computer so we can go ahead and read that serial number off of it. Doing some awesome electrical engineer stuff like connecting 2 pins to ground. Then at that point, you can't really see it here, but it has enumerated in DFU mode. Drinking more Mountain Dew before the real hacking begins. Then here's the quintessential scrolling build command running. This is actually making the firmware for the device. So just by going in the project directory, if you're looking at the Lufus source code, it's really actually, they have the make file set up rather nicely where you can run make and then make DFU to actually go ahead and program the device with the DFU programmer. So here's a successful program here of the Arduino device. Then once you unplug the Arduino, so power it down and power it back on, instead of now running either the Arduino USB serial mode or as in DFU mode, it's running as our fake screenkeeper device. So we can go ahead and plug that into the host computer here. And there you go. The screen is no longer protected by screenkeeper. Instead, the super confidential presentation involving cats has been revealed to the evil hacker. And it's a successful infiltration of that computer. So maybe a little more entertaining demo than me fumbling with an Arduino. So that's all well and good, and this had me feeling pretty good about USB assessments. I'm like, oh, this is solid. This is good stuff. I can do this. This is pretty easy. You know, it's a pretty straightforward, you know, pretty straightforward protocol. But then, of course, like any researcher, or like any time you've invested any amount of time, like doing research or presenting or anything like that, things change. And maybe they don't change drastically, but they change enough. So this is probably about 2 weeks ago now. A new screenkeeper device landed on my desk. And I was like, oh, that's cool. They made the packaging a little cooler, more like Apple-esque. But I highly doubt anything's really changed, right? I mean, this is kind of how it works or how it changes. So I figured, oh, I'll just take a look at it just to confirm, right? But now we have our new device descriptor table, right? And we can see here something did actually change. Someone became wise to this fact. And now our serial number string is no longer our super secret sauce. It's screen lock. And I was like, screen lock? That's not hex. And actually this is generic across all of the pairs. So it looks like this was actually remediated now in Screenkeeper 1.1a. So this got me thinking, well, what are still the attack vectors here? Sure, this is one vulnerability. This is one instance of what could be done. So what are some of the other things? And it really all boils down to the secrecy of this key. So now the key really isn't being sent over the USB device descriptor table. How the registration now happens is it's not on the initial plug-in of the device that it pulls out of this table that actually sets it in the registry. It waits for the first hidden message to come in, right? So it waits for a hidden message to come in and then registers that message. The problem is you can't send that, the device isn't programmed in a way to send that message unless the wireless token's in range. That's how it works. So really now we're in the situation where, as an evil attacker, we're not going to be able to go in, run in, pull out the USB dongle without the wireless token there and still disclose that serial number. So what are some other ways we could go about approaching and getting that serial number from the device? Because obviously we know what we need to do once we've obtained that serial number, so now it's just a matter of how we do that. So one way we could do this really, and maybe it's not too far-fetched, just a little mission impossible, but maybe not, is wait for someone to leave their computer, basically go to their computer and grab their USB dongle. They have their wireless token on themselves. They're walking around with it. It's transmitting to any device in range. Once we have their USB dongle, all we have to do is get in range of them to have that USB dongle then start spitting out the serial number to us. There's no authentication of what computer that's plugged into or anything like that. So we could go to a meeting with them, we could run into them in the bathroom, but all we need to do is get into range of them with that token on themselves and basically log that serial number, then go through and repeat the exact same steps we did before. So again, you still run into the issue of really there's no authentication between the host software and the wireless token. The two things that are assumed to not be compromised, there's still kind of the vulnerability of this thing's, if that dongle's in range, it's just going to send that secret to the USB device, maybe even if it's not stored directly on that USB device. So okay, you're probably saying, well, that's cool and everything, but you could also just go and grab their laptop and run out of the computer. Well, that's true. So what are some other, give me a real vulnerability. What other things could you do? So one thing I looked at was really, what's the feasibility of just brute forcing the serial number? So I went down the steps of really looking at the key space of that serial number. I kind of had a rather small sample size of these, but what would it look like to actually go through and brute force the unlocking of this? Maybe we don't even need that. Maybe we can just iterate through enough keys to unlock the device. We really need to look at the key space and the number of possible keys we would have to try. And you get the number of possible keys by looking at the number of possible symbols and the length, and you take the number of possible symbols to the power of the length. So if we look at the full HID report, we know we have a 25-byte HID report, 255 possible symbols in that, and we have like 5.7 bazillion, whatever, possibilities. Definitely a huge number that's not probably going to be feasibly brute forceable. You're trying to brute force a 24-byte key. But we can remember that they're not actually using all of those bytes. They're using it to represent Unicode text. And if we can assume that this is going to be a printable value, it's being stored in the registry, if this is a printable value, let's say we're looking at 94 possible symbols. And now we've cut our length in half because if we're just looking at printable ASCII, it's just going to be the first byte. So you have half the number of bytes. But we still have a huge number of values. 94 to the 12th is by no means small. But then we can remember looking back in all of the samples really is, it's not any Unicode string it's using. It's a Unicode representation of a hex string. So now we're down to the fact of, well, now we know we have 16 possible symbols in a hex character. We have 12 of them. So now we're somewhere around 281 trillion, which is still a lot. But then looking kind of at the different sample sets we have, do we really, are really all of those hex digits that we're going to try to brute force, are they not predictable? And we can see over here, and actually what we saw before, what's actually being stored in the registry doesn't even include those last 2 bytes. That's the 01 value that gets tacked on. So we can go ahead and get rid of those last 2 bytes, or the last 2 hex values. We don't need to brute force those. And we can see here actually, the first 3 bytes, I had a fairly small sample set, but these are from, basically these 2 were the 4 Bs were from the new set of Screenkeeper devices, and the 4 As were from the old ones. So you can assume that's somehow related to a batch number or something like that. Definitely not something that's going to be completely random or unpredictable. So if we get rid of those, really what we're left is with 16 to the 7th possible keys we need to brute force. So we can whittle it down to 7 hex digits. That's around 268 million keys in the full key space. If we consider ourselves lucky and we're going to hit averages, on average we'd have to hit we're going to have to search through 134 million different keys. So now the question becomes, how fast can we go through 134 million? 134 million when it comes to brute forcing typically isn't much of a, with modern technology, if you'd consider that key space for really anything else, it's kind of infeasible. Or not infeasible, it's kind of very feasible. It's, 134 million is really nothing when it comes to typical brute forcing. But then looking at the rate in which I could send these HID report messages, I could send them every 0.032 seconds, which turns out to be about 31.25 messages per second. So now we're getting to the point where maybe it's more of a Mission Impossible situation where I have to be an evil janitor for somewhere around, 50 days, hanging out at the computer again. Probably more likely just to grab the computer and run. Kind of with the conclusion for the brute force is while it's not very great to only have that number of combinations, as far as brute forcing goes, it's kind of an infeasible attack in this. So now I'm getting a little desperate here. And last resort, and this is dangerously approaching the EE skill set. You can see here there's actual circuits and resistors and things. Not what I signed up for when I wanted to do the USB assessment. But just kind of in next steps and things to look at this in the future, something that I didn't have time to, but definitely would be interesting to look at is this running a Nordic semiconductor chip. It's actually kind of a really cool chip. It has USB built in, has 2.4 wireless built in, basically has everything built in. But one of the interesting features it has is one-time programmable memory. And you can almost assume this is exactly where that serial number is being stored. And this memory is programmable over a SPI bus. So you hook up to a couple of pins, you hit one pin to set into programming mode, and you can read and write this one-time programmable memory over the SPI bus. So again, assuming the fact that we've physically compromised this device, there's nothing preventing us from grabbing that device, breaking it open, reading this off the SPI bus, unless there is actually a feature on the one-time programmable memory to disable any readback over the SPI bus. So really, kind of the next steps for investigation is to look at that SPI bus, make sure that that specific one-time programmable setting has been burnt to prevent that. One interesting thing from the spec, though, which I'm almost going to guess is likely what's being used for the serial number, is each chip ships out of the factory with a 5-byte pseudo-random number. Printed on it on the chip ID, and it's part of this one-time programmable memory. If we go back and we look at our keys, we have a 10-byte value. So that's likely what they're using to uniquely identify and pair and as their secret information for the chip. So that's kind of the next steps for looking at the Screenkeeper is do something like, I think there's the Bus Pirate device where you can go through, look at SPI traffic, really identify, can you read information off of it? Unfortunately, I didn't have time for hacking SPI devices with Arduino. Probably make an interesting topic someday. So again, what could be done better? Obviously, there's a number of things that could be done better. But the overall issue really is an issue with not understanding the trust boundaries, right? We can physically compromise a USB device. And in the end, no matter if it's not disclosed unless the token's in range or not, really the issue is that secret information that we need to authenticate to the host is sitting on a physical device that is assumed to be compromised. So no matter what you do to protect that, it's always going to be an issue where that can be compromised. So really the better architecture here, right, is you have a generic receiver and you have some sort of secret between the token and some sort of secret between the host software. Again, the two things that we are assuming are not compromised. And then they need to mutually authenticate to each other to say, yes, I'm not disclosing this secret to a malicious third party in each way. So that's really kind of what a better architecture for this would look like. And lo and behold, another device appeared on my desk not too long ago. And that's exactly what this proposes it does. Well, it's not what it proposes it does, but it's architected in a way where there's a generic wireless receiver now. So now we don't have a wireless token and a wireless receiver that are paired together in some sort of way and are unique and specific to a host. We have a generic receiver that can read from any of these tokens, and then in the host software, you register that token serial number in your host software, and then maybe they're doing some sort of magic to authenticate each other. And then really we're in the situation, though, where you can swap out any of these wireless receivers, so we know that wireless receiver isn't storing our secret information. So this is definitely, likely maybe they're doing something better, but we still need to identify what they're doing to authenticate each other. What is the host software doing to authenticate that device? So again, how do we go about identifying where the secret information is being stored, how is the secret information being transmitted. Unfortunately, we're back to the drawing board of going through our steps, right? So we go through and we do kind of the similar assessment, but now with this new device. Go through our threat modeling. As I mentioned, there's two components, well, three components now. There's a generic receiver that you can swap out. There's a wireless token, and there's host software. Kind of the interesting thing with this host software, it does actually integrate with Windows Login. It integrates with Gina. It's great. It seems likely more of an enterprise-y, secure solution. So it's really definitely interesting to look at and see, obviously they put in the investment to write their own device drivers. This no longer just piggybacks on top of the HID device class. You install your own drivers. It probably works on its own protocol. So hopefully they did things securely, because it seems like they've maybe taken a more mature approach to doing this. So once you install your device drivers, you plug in your USB receiver, you then can go in this configuration utility, and you can basically search for wireless tokens in range and say, that's the wireless token that I want to pair with this computer and this specific user account, and it pairs them to kind of link that information. And you can have multiple tokens assigned to different user accounts on the system, so you can have multiple people walking up to the computer and unlocking the computer. And so basically the serial number that you type in or you select from the list is printed on the back of the device, and that's fine. You're hoping they're doing something else to identify these tokens, to authenticate these tokens. They seem to taken more of a stance to really flesh out this architecture. You can also configure things like setting up a specific signal strength at where it will kind of cut off lock your screen. So you can kind of test this in your environment and say, well, here at this point right here, I'm 5 feet away from my desk. At that point, lock it. So you can kind of fine tune the signal strength at which it'll lock your host computer. So all kind of more enterprise-y, cool features in this. So, but we still really have the same use cases to look at. The first is device registration. So we talked about that installation process. What's actually being done to register those devices? What's being done to unlock the host computer? What information is being sent over USB to signal an unlock? And then at the same time, what's being done to signal a lock, to say, hey, I'm out of range, lock the computer. We know we can configure signal strength and things like that. Maybe that's part of this protocol too. So really we have the same use cases to look at, kind of in a more complex and interesting architecture. So given that, the application protocol was more complicated. We no longer have static messages. Well, we have some static messages, but the general messages when a host is unlocked is no longer static. It has things changing. You start thinking maybe this is doing challenge response, maybe this is doing things correctly. What is this actually doing to authenticate to the device? As I mentioned, it no longer registers as a HID device when you plug it in. It has its own device driver, so they wrote their own kind of, not using a class driver, but using the direct control transfer messages. They're sending that across USB to kind of communicate. And then in the initial registration, so when you plug in this generic receiver, no serial number-ish things are being sent, right? And that's kind of expected because this is a generic receiver. You can swap them out across different tokens and use them. So now we come in the case, well, now we need to start looking at this protocol. And if you've ever done a network client server assessment, it all boils down to protocol analysis, right? You have this block of bytes. And you really need to identify what's the meaning of these different values, these different bytes, and how do you go about parsing that. So kind of the first use case to look at is device locked. What's actually being sent when a device locked? And there are actual messages still being sent. The USB receiver actually maintains a heartbeat with the host software to say, hey, I'm still plugged in, I'm still here, and every 2 seconds or so, it sends a version string across. Then actually, more common than that, every 0.03 seconds, heartbeat messages are set up. So really the generic receiver is sending its version information across, even when there's no wireless tokens in range. So it's just maintaining that heartbeat. So obviously we don't have any specific messages to say unlock. So that's kind of the more interesting messages to look at. That's where we get this big table, is the unlock messages. So these are the messages that are actually sent across for a single token when it's in range of the USB receiver. This is what's being sent across the USB bus to the host software. So we have a number of fields. and I'll step through that. They're kind of grouped, about once a second, 2 messages are sent from on the USB bus from the USB receiver, and these are the messages we have. So we can see here we have a static value in the M0 column. We have what looks to be an incrementing value in the M1 column, some static fields and things like that. So going through that at the first offset in these byte messages. The first byte just represents the message type. So this identifies basically, there's a couple different message formats. Really the one we're interested in, though, is the one that's going to unlock the host. So that's the token in range. You have a token, it's in range, and that's when that value is set to 32. So that's really the messages we're interested in understanding, because we have to understand exactly what's in that message to be able to replay it to unlock the device. So the next byte in that message is actually what I'm calling the USB counter. So for every message that's received by the USB receiver, be it from multiple tokens or for an unlock for a token in range message or things like that, it increments +1 every single message, and it rolls over at FF back to 0. The interesting thing is if you unplug the USB receiver and plug it back in, this rolls over to 0. So we can assume, well, if we're in the situation where we're, again, trying to plug in our malicious device, we know this value. We know that's going to start up at 0 again. So there's nothing there that we're going to have to brute force 255 different values to sync up at the right place in this counter. So it's good to know that this counter rolls over, starts over at 0, so we can replay that. It's a predictable thing when we plug in our malicious device, if it gets to that, of course. The second offset, index 2, is all nulls, so obviously we can predict and replay that. Bytes 3 to 4 actually aren't very obvious. If we look up back at this slide, 3 and 4 actually seem to be floating around FE, FD, but actually looking at a long log of these messages, there doesn't really seem to be any correlation. It's not a counter, it's not things like that. So really that requires a little more investigation, what those 2 bytes are controlling or what that means in the protocol message. But we'll get to that. The 6th byte at offset 5 is your token counter. And this is similar to the USB counter, but it's unique per token. So as I mentioned, multiple tokens can be sending messages to the USB receiver. And this token counter actually only works on a nibble. So it's 40 through 4F and then rolls over. So even looking at this, if we're in the case of, well, we want to replay these messages, we're going to want to spoof these messages, worst case scenario, we're only going to have to brute force 16 values to get at the right value of the current counter. So that's also promising of, well, we have 16 values we're going to need to try to send a valid unlock message to sync up with this counter value if that counter value the state of that counter value is being maintained. And this number does change for different events. Each of the tokens have like an on and off button, things like that. And when you press those buttons, different values go through for this token counter basically to signal someone pressed the off button, someone pressed the on button, and it does logging of these things. M6 is another null byte. And then we have our last 3 bytes. So what this actually is a 3-byte identifier. It's unique and static per token. So this is sounding a little familiar, right? We now have a static token identifier in this message, and it's unique and static per token, so it's the same value being sent for each unique token. And actually, if we look at it, here's examples of the different token numbers I had printed on the back of my wireless token, and also what was shown up in the configuration utility to pair these devices. These are the 3-byte values, so it's just the hex representation of that actual token ID. So again, we now know exactly what that is. That's the identifier for the specific token. So this could be bad, right? Is this doing the exact same thing of just in its protocol messages, sending its token identifier and using that to authenticate without really any other authentication? But we have to look back and say, well, we still have those 2 unknown bytes. Maybe that's doing something to authenticate with the host. Authenticating with 2 bytes definitely doesn't seem like a good idea, but maybe it's what it's doing. So let's take a kind of a deeper look at those 2 bytes. In the traffic, they really seem to vary randomly with each message. But one thing to remember is, well, as part of the UI, we can see the signal strength. We can set up different lock states for different signal strengths. So to test this, I was like, well, what happens if I just take this dongle and walk across the office and walk back? What does that value become? And we can see here, what we actually get is exactly that. So this is the highest value here when I'm at my desk. Again, walking away from my desk, you can see the value decrease, and as I walk back to my desk, it increases. So that's exactly what these 2 bytes are controlling, is just a representation of the signal strength to tell the host computer, this is your current signal strength. You have thresholds set up for when to lock and when not to lock. So now we're at the case of, well, there's no more bytes left in these packages, these packets. There's really nothing else here. So we're in the exact same summary, or the exact same situation we were before. Sure, we have a generic receiver, but we have these tokens just being sent, and that's all that's really being done to unlock the host. We know the bytes 7 through 9 are the token ID, and the question becomes then is, well, this is now our new secret. This serial identifier that's printed on the back of the token. So worst case scenario, you can just go up and be like, hey, that's a sweet token, and look at the token and get that value. So really, there's nothing preventing that from being physically disclosed if you can look at the token. But also remember, we can run our configuration software. These receivers are generic. There's nothing preventing these wireless tokens from just sending that serial number across in protocol messages to any receiver that's in range. So as an attacker, all you have to do is just sit within range of one of these tokens, sniff the identifiers, then replay this traffic with that new token identifier in. And I actually did this. I didn't instrument this in Arduino, but I used a USB protocol analyzer and generator to do just this, to send the exact same unlock requests with the modified token identifier. And again, just looking at the protocol, there's nothing preventing this from going through and unlocking a host. So really kind of we're in the situation that's almost worse than before. All we have to do now is just stroll around the office and get everyone. We don't have to go through unplugging all their USB devices. We can just walk around with our laptop and our receiver and really get everyone's identifier, go through, replay this traffic with our modified 3 bytes and unlock the host. So again, it just seems to rely on the fact that no one will figure out what this is doing, or maybe it's just our trust model and what can be compromised definitely changes here. Now we're not worried about that USB device being compromised, but really it's the fact that these tokens are just broadcasting out their secret to anyone who's listening. The interesting thing is, all this can be kind of gleaned from, I didn't have to start looking at this wireless traffic. This is just, by looking at these USB protocol messages, kind of the easiest route to take. I don't have to go out and buy a GNU radio or anything like this and start understanding the wireless protocol. All you really have to do is understand the USB protocol because of how we're crossing these trust boundaries and disclosing information where it shouldn't be. So really, this all, again, boils down to the disclosure of the secret information. Instead of now having a Post-it note with your password in, you're screaming out your password to anyone who's listening. So really, not a good implementation, even though there are high hopes in just how it was architected. Really, in these situations, you need to assume that the USB device has been compromised, that even though they covered that. What's really lacking here, then, is the authentication between the 2 components. This, if there's a shared secret, those 2 need to keep those secret to themselves and derive a message from that that can't be sniffed and replayed and things like that. And that's really kind of what the architecture is missing. And then, that secret really needs to be secret to everything except for those 2 trusted components. So, this is kind of the equivalent of, just kind of the not understanding what's client controlled or what's being disclosed. I look back to web apps, and everyone's run into the web apps that has like the cookie set with your username. It's the web app 101 kind of like, of course you don't architect it this way. Of course a user controls that. Of course someone else could see that. So really it's just, in doing this USB assessment, it's kind of refreshing to see, the same mistakes are being made now just over a different protocol. So once everyone figures those out in web apps, there will always be people making USB devices with horrible protocols to look at. And really, the process is exactly the same. If you just step through, identifying the different components and really understanding the trust boundaries and the use cases and how those use cases are implemented, it's the exact same thing you would do during a network, client-server assessment or a web application assessment. So now, I wouldn't say the new life, maybe the new life for a week or so, is I could stroll into work, fire up a USB analyzer, sit in front of a USB device. At least now I get to like walk out of my cubicle to test things, analyze stuff, flash firmware, break stuff, and report. So it's all the same thing, just a different protocol. Definitely there's freely available tools and cheaply available hardware to go about doing this assessment. So it's definitely something interesting, and I'm glad I had a chance to look at some of these interesting devices, to look at it, and it just kind of makes you wonder, you have these hardware devices, they're kind of closed systems. It really becomes, well, what are they doing and what are they doing wrong? And it becomes just the same, as looking at a different application. So thank you for coming by. Does anyone have any questions? Sure. At the end for the proof of concept, yeah. It would be the exact same thing in the Arduino. I mean, oh, what device? Yeah, it was the MQP Packet Master. It's actually a really nice device. You can log traffic, and then from that traffic, just say like, give me a script. It creates a generator script, and then you can go through and modify it and add loops and stuff. I wish the scripting language was a little more flexible on conditionals and things like that, but it's great just for, again, just to validate, without having to go out and do a full proof of concept. Thank you.